So let's continue this day, and now we are going to listen to Roland Bauerschmidt giving his second lecture on Log-Sobolev inequalities and renormalization. Okay.
Okay, thanks for coming back. Let me quickly recap what I discussed last time. So we're looking at stochastic dynamics of the simplest type, and in fact on finite dimensional state space, Rn, but we think of n being a large number of points ultimately approximating, say, Rd or Zd. The type of models we have in mind are either lattice models or continuum models with a focus on continuum models. So those are ones for which this dynamics would be an approximation of an SPDE. And so the two prototypical examples I have in mind are, say, a phi-4 model, which would be this case, or a Sine-Gordon model, which is the second one. So maybe I should add so I'm not actually going to talk about the phi-4 model. It's not something we can do, but here the dimension should be between 2 and 4. I should perhaps add that. Maybe at this point I should mention that it's a good exercise to just look at this model in one dimension, in which case these counter terms that I mentioned here, these divergent constants are not necessary. So all coupling constants are finite. And in fact, we already discussed all tools to, say, study the Log-Sobolev inequality for those models in one dimension, at least in finite volume. But as I discussed also in higher dimensions, there are these counter terms which are divergent, and that's what we'll be looking at today. Then we discussed the celebrated Bakry-Emery theorem, which is a very simple criterion for the Log-Sobolev inequality to hold. And it's basically just asking for the potential H to be strictly convex. And if it is with Hessian bounded below by lambda, then also the Log-Sobolev constant is bounded below by lambda. Maybe I should, for future reference, say that equivalently, we could write the condition that the Hessian of H is bounded below by lambda as A is bounded below by lambda, and V is convex. So or maybe let's say Hessian of V is not negative. So if we write the measure as e to the minus 1/2 phi A, phi minus V.
Roland, there is a question in the chat.
Yes. You mentioned De Bruijn inequality about the relative entropy with respect to the invariant measure decreasing over time. Do you know under which conditions we have a gradient flow on the relative entropy? Okay, let's maybe postpone this question. It's a little bit not, it's not the direction I want to focus on. So maybe let's postpone that to the break. That's okay. Okay. Okay, so this is where we stopped, and or not quite where we stopped. We stopped discussing a few properties of Gaussian integrals. More precisely, we were looking at a covariance matrix that depends on a parameter S, Cs. And and we wrote that covariance matrix as an integral over another covariance matrix, C dot S, which I again assumed to be a positive definite matrix. And the canonical example that we'll be looking at is where this C dot S is in fact given by the heat kernel e to the minus SA. So remember, we're thinking of A as a Laplacian. And so I'll be calling this a heat kernel. Okay. And then we saw that, in fact, okay, well, the Gaussian measure satisfies the heat equation, as you probably knew before. We need this version where, I mean, the Laplacian or the appearing in the heat equation is actually dependent on time and has this symbol C dot S, which is just given by this infinitesimal covariance matrix. Okay, so this is now really where we stopped. And before moving on, let me just, we're not going to need these so much, but let me just mention a few consequences of this. So first of all, basically immediate obvious consequences. If you define a function fs to be the convolution of the Gaussian measure, PCS, with some function f naught, or saying this a different way, fs of phi is the expectation with respect to this Gaussian measure of f of phi plus zeta, where this Gaussian, where phi is fixed and this Gaussian measure applies to the variable zeta. Where then, of course, f satisfies the heat equation. And in particular, if we take fs of 0, that is just evaluating the Gaussian integral with covariance Cs of f. Okay, so this is a sort of almost tautological consequence. Another useful consequence, also immediate, is if f is a polynomial in our variable phi. So if f is a polynomial in phi, then, and this you may call this Wick's rule, then fs is, well, it's the solution to the heat equation, which for polynomials you can just write as e to the 1/2 c Laplacian with the symbol cs applied to f naught. And so here, by this exponential, I really mean 1 plus 1/2 Laplacian cs and so on. This is terminates after finitely many terms, since f naught is a polynomial, and it gives a bunch of terms which are again which is again a polynomial in phi, and that's this Gaussian convolution. You could also view this I guess exercise or another corollary as you wish. So again f is a polynomial. Then you could define what is called the Wick ordered version of f by running the heat equation in the wrong time direction. Now, so this is called Wick ordering. Now, generally, you should be very careful when running the heat operator in the wrong time direction. This is already the second time I'm doing this. But again, there is absolutely no problem here. F is a polynomial, and this is defined in exactly the same way as up here, right? So there's no problem. And what you can then see is that if you take the expectation or the Gaussian convolution of the Wick ordered version of f, well, you just recover f. And in particular, the expectation of the Wick ordered version of f is just given by f evaluated at 0. Similarly, I guess I'm running out of space here and I don't want to start a new slide for this, but let me just mention this. So similarly, if you have two polynomials, say f and g, let's suppose they're both homogeneous and their degrees are not the same. Well, then the expectation of the product of these polynomials is 0, so they're orthogonal. So these are all properties that you probably know. I just want to advertise this point of view of just using the heat equation, run backwards or forward in whichever way is convenient to see all these properties, because they're basically completely immediate from this. So for example, the orthogonality and so on, you can just read these off from these formulas for exponentials. Okay, so this was just a little cultural digression. Before I will move on to the perhaps most important topic of these lectures, which is the so-called renormalized potential. So the renormalized potential is defined as follows. So this is, I will define Vs, which is a function of phi, to be given by one of the following, I guess, three equivalent characterizations. So one is, I define it as the convolution of the Gaussian measure with covariance Cs with e to the minus V naught, where V naught is now just our original potential V, which I'll be calling V naught. Or said in an equivalent way, this is the Gaussian expectation with respect to the variable zeta of e to the minus phi, e to the minus V naught of phi plus zeta. Okay, so this is the one characterization. Another one would be to say that e to the minus Vs is a solution to the heat equation with the symbol Cs dot and initial condition Vs at s equals 0 given by V. And yet another way is to say that Vs satisfies what is often called the Polcinsky equation. So that is to say that Vs satisfies the following nonlinear heat equation. So let me here recall this notation that I sort of used last time before. So if I'm taking two vectors u and v, and I have this inner product Cs dot, that's just meaning sum over all x and maybe y, and take Cs dot x, y, u, x, v, y. And okay, so this is called the Polcinsky equation. Okay, so okay, let me I'll tell you why this is Well, I'll first tell you why this renormalized potential, defined by any of these three essentially equivalent ways, is a useful quantity in just a second. Let me just point out that if you look at e to the minus v, well, that satisfies an, well, essentially trivial looking equation. It's a linear heat equation. Well, if you're looking at Vs, it satisfies a somewhat more frightening equation because it's a nonlinear heat type equation. So I guess what's going on between this going from the exponential to Vs is something similar to, or more or less, the Cole-Hopf transformation, right? You see something that looks like maybe a Hamilton-Jacobi term here in this minus gradient Vs squared. And then we have some kind of diffusion or viscosity term in addition. But really, okay. Okay, so let me, before dwelling on with this, let me just tell you one nice property, which is the following. So suppose Vs satisfies the Polcinsky equation. So maybe I should give this a name. And suppose also that fs, where f is another function, satisfies what is basically a linearization of the Polcinsky equation. So it satisfies this equation. It depends on Vs, but as a function of f, it's a linear equation. So it's a linear operator depending on S through Vs, but then acting linearly on this function f. Well, then, I guess I need to try making some space here. So let me delete or move these maybe up here, and the arrows will be fixed later. Okay, so then the following is integral. The following integral is independent of S. And that is the integral of the Gaussian measure with covariance C infinity minus Cs of e to the minus Vs of phi, and then putting in Fs of phi. So the claim is this integral actually doesn't depend on S. Okay, so move this to the next slide. Okay, so how do we see this? The proof basically only takes a line. So how do we see it? Well, define, let me call this Zs of phi to be e to the minus Vs of phi, Fs of phi. Well, then actually this satisfies a linear heat equation. If F is equal to 1, then, well, this is just the fact that e to the minus Vs satisfies the linear heat equation. Well, if F is not equal to 1, well, this is exactly what this definition of F achieves. So then DDS of Zs satisfies linear heat equation. So hence, if we differentiate that integral, so we differentiate. Well, the derivative in f can act either on, well, on the Gaussian measure or on this combination e to the minus VFS. So if it acts on the Gaussian measure, well, we know the Gaussian measure satisfies a heat equation, but I've put in the time parameter with a minus here. So this is the covariance C infinity minus Cs. So this actually satisfies a heat equation in the negative time direction. So the time derivative of this is of the first term would be minus 1/2 Laplacian Cs dot P C infinity minus Cs. And then it's multiplying the rest, which was called Zs. And then there's the other term. So there's another term plus. So we get the measure C infinity minus Cs. And then we get the derivative of Zs, which is a heat equation within the positive direction. Okay, so all of this is integrated. Since it's integrated and all terms decay at infinity, we may integrate by parts and see that the two terms actually cancel. So the derivative is 0. Okay, so that's the proof. This integral is independent of S. I could have derived this for you also in a, I think this is the conceptually nice way to see it, but I could have also derived it maybe in a more hands-on way. I will define this combination of measure of this Gaussian measure and the and this renormalized potential. We'll call this the renormalized measure, nu s of d phi. Maybe include the d phi as well, or not. So I will call this nu s of phi, and I will call fs of phi also p0s of f naught of phi. So I'm thinking of fs as the evolution under some semi-group p, time-dependent semi-group from time 0 to s of this observable f naught. And in fact, you can just see that, so we have this, the renormalized measure nu s d phi is just given by c infinity minus cs of phi e to the minus vs of phi d phi, and the renormalized and okay, so that's a renormalized measure, and the semi-group is what I'll call the Polcinsky semi-group. So p from some scale, or I'll sometimes say time, but this s is sort of a fictitious time. It's not. It doesn't have anything to do with the time of the original dynamics. This you can check is explicitly given as follows: e to the plus vs of phi times the Gaussian expectation with covariance cs minus cs prime of e to the minus vs prime of phi plus zeta and f of phi plus zeta. And as before, all Gaussian expectations, they act on the variable zeta. So, and from this definition, it really is manifest that the expectation with respect to the measure nu naught is just the same as the expectation with respect to the measure nu s applied to p0s of f. So these e to the plus and e to the minus vs terms and so on just cancel out. And moreover, you can just, you can now differentiate the measure nu s and this semi-group p s prime s and all of these s and s prime parameters. And what you'll see is that this is consistent with what I was assuming before, namely that the expectation, so if you differentiate this measure nu s and s, what you get is minus the expectation of nu s, then this operator ls, which we saw on the previous slide. Let me recall this here. So it's 1/2 Laplacian cs dot minus gradient vs gradient cs dot. So the derivative of this renormalized measure is given in terms of this operator ls. And similarly, if we differentiate the semi-group, so we can differentiate in either s or s prime. If we differentiate in s prime, what we see is, let me first differentiate in s. What we see is ls applied to ps prime s into f, and if we differentiate in s prime, similarly, we get p s prime s of l s prime applied to f. And I guess there's a minus here. Okay, so let's see, what time is it? Okay, there's a couple of more minutes before the break. So, but let me perhaps Okay, so maybe I'll take a break a minute early, and I'll start a few minutes early as well, because this would be a natural point to take a break. Let me just summarize in one sentence. What we've done is we've defined this renormalized potential Vs, and can be viewed in different ways. We've seen in particular that this effective potential satisfies the so-called Polcinsky equation, a nonlinear heat type equation in many dimensions. And that then associated to this Polcinsky equation, there's a natural semi-group which is given in terms of these time-dependent generators Ls, which just linearize the Polcinsky equation basically, and sort of define a flow relative to these renormalized measures, which we defined in this explicit way. And so basically, what we have at this point is, well, we started out with a semi-group, which was the Glauber dynamics associated to the model. Now I've defined another semi-group. Well, this one is time-dependent, but it looks a little bit similar, but I'll tell you, physically, it really behaves very differently from the original Glauber dynamics. And what I'll tell you after the break is how we use this semi-group rather than the original one to prove the Log-Sobolev inequality and get much better conditions by doing that, which are in particular are suitable to handle these or to allow these non-convexities introduced by the counter terms. Okay, so I'll take a break now, but I'm happy to answer any questions during that break.
Roland, do you want to answer the question? It was remained.
Okay. Oh, actually the break was supposed to be in 15 minutes. Oh, right. Okay.
Yeah, you have.
Okay. Okay. Yes, I thought we started at 4. I think. Okay, good. Then we may continue.
Yeah, I didn't know if you wanted to stop earlier for some reason.
No. Well, I just somehow thought we started at 4, and I had the impression that 45 minutes went by extremely quickly, but I'm glad to know that there was only 30 minutes. Okay, so let me do that promised summary then. Okay, so we have a summary. These two semi-groups. So 2 ways to evolve the measure. One way, so I use a subscript for the Glauber evolution. So the measure at time t, according to the Glauber evolution, is given by evolving the density ft with respect to the invariant distribution according to what I called the Glauber semi-group. It's given in terms of this generator. Or I also wrote as Laplacian h applying to ft. So this is Glauber dynamics, continuous Glauber dynamics. It tends, at least in finite volume, it always tends to the invariant measure, which is given by nu infinity, which was e to the minus h. Okay, so this is one way to evolve a measure. We start with some measure nu equal to nu naught, and then we evolve it according to time, corresponding to that stochastic evolution, and we see this measure evolves and eventually tends to the invariant measure. The question we want to understand is how fast does that happen? Now, the other evolution I just introduced, which where I used S for the time rather than T, and to distinguish or make the distinction a bit more explicit, I'll use a superscript rather than a subscript. So I'll call this F superscript S. I'm not sure if I did this on the previous slide. Maybe not, but anyway, I will do that now. So the measure at the, let me say, scale S is given by, well, taking F and then running the Polcinsky semigroup and taking as reference measure the renormalized measure at scale S. So we have Fs evolves according to the Polcinsky semigroup. Here I have slightly different conventions here. There's a factor 1/2 here because of where it's the natural normalization here, but this is not important. I guess there should be an Fs here, and then we have an Fs here. So this is the Polcinsky semigroup. Now, from far away, they look pretty similar. They both have a Laplacian in it, and they both have a kind of a drift term in terms of some potential. One difference you'll notice is that the Polcinsky semigroup is time dependent. In fact, the potential is not always the same. At scale S, we use the renormalized potential associated to scale S. And equally importantly, the diffusion term, the symbol of the diffusion term, which in the Glauber semigroup is always the identity corresponding to this local evolution, is also changing and becomes this heat kernel. So it becomes increasingly spread out in space. So from this, you may guess that it, well, may not be apparent, but it behaves really quite a bit differently. And in fact, if you look at the long time behavior of this Polcinsky semigroup, well, it is arranged in exactly such a way that this measure, nu S, converges to some terminal measure, which I'll denote by nu superscript infinity. But this is not at all the invariant measure. This is just a delta measure at 0. So while if you run the Glauber semigroup, you eventually converge to the terminal invariant measure. If you run the Polcinsky semigroup, you eventually converge to a measure at 0. The picture is that this Polcinsky or renormalization semigroup basically loses more and more information of what's happening at the different length scales until in the very end, there's nothing left and you just have trivial information. So somehow, well, both of these evolutions, of course, lose information. No, that's the second law of thermodynamics or so, if you want, the decreasing of the relative entropy. But here it happens in a rather different way in the sense that we see how the scales, it happens in a scale by scale way. And okay, but it comes with a caveat, which is that, the Polcinsky semigroup, it involves these renormalized measures, nu S. And if we want to say anything about it, or not anything, but for many things we want to say about this, well, we need to know how this renormalized measure, Vs, behaves. What can we say about it? There's a few things, in fact, where you don't really need to.
There were two questions on the chat. Maybe.
Okay, are the superscripts correct? Let me see.
The formula d nu s equal to d fs d nu s looks funny.
Oh, okay. So okay, so indeed, let me see how I wanted to write this. Let me call this like that. We have this reference. Okay, so okay, maybe Okay, maybe I'll write it like this. Neither one is really, I don't want to put too many indices, and somehow this happened in consolidating some indices which aren't important here, but I want to keep the distinction of the two evolutions. So we start at time, the way I want to think about it, I start at time 0 with some measure nu 0. So, so at time 0. And then I change the scale, that's the superscript. And then I get this measure, and you should think of d nu s as the equilibrium measure at scale s. So maybe I should have really written it like this. Maybe that would be more accurate. So yeah, I think this is clearer now. So on the one hand, we have the evolution in time, the Glauber dynamics. We start from nu 0, we go to nu infinity. On the other hand, we have some measure nu 0 or maybe nu t. And then we change in a different direction, which is the scale direction. So somehow I don't want to, I mean, there could be this index t or not. It's, okay. Is that clearer? Maybe.
Yeah, it seems to me. I don't know to Henrik. Yeah, I think it's okay.
Yeah, I'm sorry I maybe explained this a little bit in a confusing way, but really there's a diagram I have later on. We have two directions. We have time and then we have scale. And you can either move in time or you can move in scale. And so in the first direction, we move in time, and here we move in scale, and time doesn't play a role.
Yeah, and then there were this question about the limit of Vs as goes to infinity.
Okay, satisfy some, does the limit of Vs, okay, let's, so this is the limit as s goes to infinity. Maybe let me answer this in the following way. The way I have set things up, there is a certain scale s after which things become essentially trivial. This is because we're in finite volume, say, or we have a mass term, either one would do. Once you reach a scale which is associated to mass or volume, basically these cs dot become 0 effectively. So after that, not much happens anymore. And the measure becomes basically the delta mass at that point. So the renormalized potential will go to something that is associated with this effective terminal scale, but the Gaussian measure will not contain, I mean, the covariance will be effectively 0. So as long as the Vs doesn't blow up, since the Gaussian measure goes to 0, by construction, the whole measure will go to delta 0. Not sure if that answers your question, but so remember, this is all in finite volume here. Okay, so if that's okay, let me move on. I want to, so okay, as I emphasized, we need to know something about this renormalized potential to use this dynamics. That's the whole point. There are some things for which you wouldn't have to know anything. Say that the maximum principle associated. So these operators LS, they satisfy the maximum principle. That is manifest. You don't need to know anything about the Vs for that. But and in fact, that applies the following. This example is not really why we're doing all of this, but I think it illustrates nicely. So if we start with a convex potential, well, then the claim is this potential remains convex. And so let me give you two proofs. So the first proof goes as follows. You write e to the minus Vs of phi. Well, by definition, it's given by the integral of maybe a Gaussian measure Zs, Cs inverse, zeta minus V naught of phi plus zeta, d zeta. Now, so d zeta. Now, if V naught is is convex. This whole thing is a log concave and both variables. So e to the minus Vs is the marginal of a log concave measure. So it's log concave. That means Vs is convex. So that is the Braskamp-Lieb inequality. Marginals of log concave measures are themselves log concave. Okay, so this is one proof, and I'd like to present a second one just because I find it illustrates sort of this dynamical point of view, where we know, which is that you can also see this as a consequence of the maximum principle. So Vs satisfies the following Polcinsky equation. So we want to know what the Hessian of Vs is. So let's just differentiate. So first, take the gradient. And you see, okay, if you take the gradient, what can happen? The first thing, the gradient just moves through, right? In the second term, well, the second term is nonlinear, so you get two terms, so that cancels the 1/2, and you get basically gradient Vs times the Hessian of Vs, Cs dot. And if you stare at this for a second, this is nothing but Ls applied to gradient of Vs. So the gradient of Vs evolves according to a linear equation. Well, linear given Vs, or given the gradient already. So it's not really, it's a non-linear equation, but it's sort of, it involves this, linear operator, which, okay. Anyway, it's a nonlinear equation, but you can use the maximum principle for Ls if you want. So similarly, you can differentiate again. You get a formula for the Hessian, and the formula for the Hessian is slightly less pleasant, but you see that the Hessian, so the derivative of the Hessian of Vs is given by Ls applied to the Hessian of Vs minus, and then you have a quadratic term, Hessian Vs, Cs dot Hessian of Vs. So all of these are sort of nonlinear heat equations, and you can use the maximum principle. And maybe this is a good place to take a break. And then after the break, I'll conclude, or maybe let's postpone the break for 2 minutes so I can well, 5 minutes so I can conclude this argument. So I'm claiming that once you have this, this equation for the Hessian, you can conclude using the maximum principle. So you need the maximum principle for symmetric matrices, but I'll just show you what happens if you only have one variable where the ordinary maximum principle suffices. So if you only have one variable, then this equation for the Hessian is simply the following equation. It's the equation ds. So I'll denote by fs the second derivative of vs, so the Hessian, which is just a function of one variable now. So that satisfies the equation ds of fs is ls of fs minus fs squared. Well, by the maximum principle, if fs is non-negative, well, so is so the maximum principle asserts that if f is non-negative, then ls of f is non-negative. So from this, you can see that the derivative of fs is bounded below by minus fs squared, which is assuming that f naught is greater or equal to 0. And from this, you can, as equation one variable, you can integrate and see that fs remains non-negative all the time. Okay, so this concludes the proof in one variable, and for general n, you need the maximum principle for symmetric matrices, or how it seems to be called in the literature, the maximum principle for symmetric tensors. Okay, so this is a good place to take a break. And after the break, I'll continue and we'll show you how to use this renormalized potential to get an improvement on the Bakry-Emery criterion that will work in the settings, or at least in one of the settings we're interested in, where the potential looks rather non-convex. Okay.
Okay, thanks. So let's take this 5-minute break.
Okay. 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 So taking a break is always a good opportunity to remember a few things that I maybe should have mentioned but didn't. So let me do that now. One is, of course, this idea of studying the renormalized potential is not at all new. It's very well developed in theoretical physics. In particular, it goes back to Wilson. And he mostly looked at, rather than this continuous flow, he mostly looked at discrete steps, though not exclusively. And maybe the physics paper where this continuous point of view was exploited in the most beautiful way is this paper by Polcinsky, which is really a very beautiful paper, in which he among other things, writes down this equation and uses it to study the phi-4 model and in the perturbative fashion that is as in terms of as formal power series in powers of the potential defined order by order. Okay, so that's something I should have mentioned, but good. Right, so I just showed you, so we defined the effective potential. I showed you two ways in the case that we started with a convex potential to see that we remain with a convex potential. And so in that view, so this is our first theorem, which is with Thierry, which is as follows. So we assume that the matrix A, my parametrization of the measure is bounded below by lambda times the identity. Lambda is not negative, positive, in fact. And we assume that the effective potential is bounded below in the following way. So I'm taking the Hessian of Vs, and then I'm applying this matrix Qs, which is just the heat kernel on both sides. And we assume that uniformly in phi, this is bounded below by some constants, which I'll call mu dot s by the identity. And the conclusion is that then the Log-Sobolev inequality holds, and that the Log-Sobolev constant gamma is given in terms of this formula for 1 over gamma as the integral of 0 to infinity e to the minus lambda s minus 2 mu s ds, where mu s is the integral from 0 to s of mu dot S prime. Okay, so so let me make a couple of remarks. So the first remark is, or one point I need to emphasize is that these mu dot S, they're allowed to be negative. So all that matters is that this integral converges. So everything is, of course, well, the Log-Sobolev inequality holds provided that integral is finite. So the condition QS Hessian VS QS with the QS on both sides may look a little bit, well, hard to interpret with the 2S, with the QS on both sides, but really the QS on both sides is the heat kernel, it's smoothest, it only helps to verify the condition. And in fact, in terms of this interpretation, in terms of a Riemannian metric that I mentioned before, so if you interpret this in terms of the Riemannian metric GS, which was e to the plus SA, so the inverse heat kernel, the condition is just that the Hessian in this metric is bounded below by mu dot. Another remark is, well, just tying to the example I just presented, if V naught is convex, well, then we've seen that Vs is convex for all S, and this just recovers the Bakry-Emery criterion. Indeed, you can just choose 8 to be lambda times the identity. V is H minus 1/2 phi A phi. Then by assumption, V is convex. And we know that the mu S dot is non-negative for all S. And so the Log-Sobolev inequality holds with constant 1 over gamma given as the integral from 0 to infinity, e to the minus lambda S. The mu dots and mu's, we can, here these we can drop because they're non-negative. And so this is, so this is, and this is given by 1 over lambda. So maybe this should be bounded above. So we get exactly the Log-Sobolev constant, the lower bound on the Log-Sobolev constant given by lambda S in the Bakry-Emery criterion. But the main point is, of course, that, well, Vs doesn't have to be convex, and that in many cases, even if we start with some potential which looks rather non-convex, that Vs becomes improves as you move through the scales. So in fact, this Vs is, it's not necessary that ultimately, so in simple cases, it will ultimately become convex, but it's not necessary. And in fact, it suffices as long that this Hessian of Vs is sufficiently controlled. Okay, so maybe here, before I show you the proof, maybe let me mention a couple of exercises. Or maybe, let's see. I'll do the exercises after the proof. That sort of allows me to so the proof is really very much the same as for the Bakry-Emery argument. So it's almost the same. So it's like a Bakry-Emery with a few minor, or with a few minor, but or subtle but very important differences, of course. So it's just like Bakry-Emery, but we use the Polcinsky semigroup rather than the Glauber semigroup. And so the starting point of the Bakry-Emery proof, if you remember, was this De Bruyn formula, which allowed us to compute the derivative of the relative entropy with respect to time. So now we'll compute the derivative of the relative entropy with respect to scale. So remember this, this new S is the renormalized measure. So in the so we compute this derivative with respect to scale. So this is like the starting point of the Bakry-Emery proof, except there the measure wasn't actually changing. We were always computing the entropy with respect to the invariant measure. So here our measure is changing, as is the relative evolution Fs. So we compute this derivative. So what happens? So first, the derivative can act on the new S or it can act on the Fs. If it acts on the new S, we have seen that this derivative is given in terms of this generator Ls, and then it applies to phi of Fs. And then the other possibility is that it acts on Fs, in which case we get the derivative of phi and then Fs dot. So now dot is denoting the derivative with respect to S. So, so let's try to simplify this expression. So Ls, remember, is sum of a Laplacian with the symbol Cs dot plus a drift term, which is a first derivative. So what happens is that so if we look at the we get the following result. Let me write it down and then. So the derivative, so the first derivative will always have to use the chain rule to differentiate phi, but then all derivatives act on Fs, but there's also a possibility that the second derivative we're taking is acting on phi again. So we get a second term, which is the second derivative of phi evaluated Fs. And then we have the gradient of Fs squared Cs dot. These terms are the ones that come from the first term. And the second term is plus phi prime of Fs. This is not F prime, Fs. And then we have F dot S, which so this Fs is evolving according to. So this is the Polcinsky, what I'll call the Pulzinski flow. So it evolves according to the Polcinsky semigroup. So therefore this Fs dot is just given by Ls Fs. And we see that the first and the last term cancel. So we're only left with this term involving the second derivative of phi. The term with the second derivative of phi, well, the second derivative of phi turns out, so phi is, you recall, phi is x log x. The second derivative of phi is 1 over x. So we have a version of this De Bruyn identity. So I might also write this as -2 times E nu S times gradient of square root of Fs Cs dot squared. So we have a version of a De Bruyn identity, which I recall gave the derivative, time derivative of the relative entropy in terms of this quantity, which is often called the Fisher information. So here we have a version of this Fisher information, which however also depends on the time parameter, which is scale now, S, because you see the quadratic form that appears here is S dependent. It's not only F that's S dependent, but it's also, okay, maybe I'll write this down here. So this is sort of a Fisher information at scale S. Okay, so this was the first step of the Bakry-Emery argument. We use this De Bruijn identity, and we have a very good replacement now. It looks exactly the same, with the only difference that the Fisher information is also dependent on scale. And okay, so now the next step is the next step in the argument is well, the next step was to differentiate again, right? So consider change of the Dirichlet form. Oops, what's happening here? Change of, so in this case, Dirichlet form is, I think I'm getting a little bit, I'll sometimes write the superscript S as a subscript. I think I won't be 100% consistent, but whenever it's an S, it's scale, and whether it's a subscript or a superscript. So anyway, so we do that. So we compute the following. So this is, so this is what appears in that scale-dependent Fisher information, if you want to call it this way. So that's this quantity, and we compute the time derivative, and then we also subtract the scale-dependent generator. So that accounts for differentiating the measure roughly. Okay, so now there's various places the derivative can act. Well, first of all, the S derivative can act either on the function here, or it can act on the covariance, which is here. The quadratic form. So let's do this where it acts here first. So for that, we get one term, which is plus the gradient of Fs squared Cs double dot. And then we get the rest. And the rest, so for the rest, the computation is exactly as if the Cs dot didn't depend on S. And so that is exactly the Bakry-Emery argument. And it's this tedious exercise, which I'm not sure you did, tedious but elementary exercise, for which the result is the following. So I'll write this down. It's exactly the same computation as before. The prefactors of 1/2 and so on changed a little bit since we've normalized the Polcinsky dynamics has 1/2 in front of the Laplacian and so on. Okay, so that's the result of this computation. And what is CS double dot? Well, remember CS dot was given by the heat kernel. So CS double dot, well, this is trivial to differentiate. We get minus A times CS dot. So let's substitute that in. Let me make a little bit of space here. Okay, no, the space is okay. So again, as in the Bakry-Emery argument, this term is manifestly not negative. We'll drop it to get an inequality, which now involves the first term and the second term. And to make this look a little bit nicer, I'll write as in the statement QS for the square root of CS dot, which is just e to the plus S, or e to the minus SA over 2. So in that notation, what we have obtained is gradient square root Fs. Then I'll write QS bracket A plus 2 QS Hessian VS QS bracket closed QS gradient square root Fs. Okay, this is what we obtained. And we see that, well, our assumption was, well, it was that A is bounded as a quadratic form by lambda times the identity, and that QS Hessian vs QS was bounded by mu dot S. So this is the assumption. Okay, so in summary, what we've seen is that DDS minus LS applied to what to the gradient of the square root of Fs with this moving quadratic form CS dot is bounded by minus lambda plus 2 mu S dot. The expectation of what we there's no expectation here, in fact. Okay, so this is what we got. So we have the same kind of contractive bound as in the Bakry-Emery argument, with the only difference that it involves the the renormalized potential rather than the original potential, and that the quadratic form, the CS dot, moves as well. But from this, it's the argument can be concluded in the same way.
Maybe a square is missing on the right hand side, no?
There's a square missing, indeed. Thank you.
Hendrik observed.
Yes, thank you. So the proof can be completed in the same standard way. So let me just do that. So if you define a function psi s as e to the expectation nu s gradient of square root Fs Cs dot squared, then this function satisfies by the above computation that its derivative is bounded by minus lambda plus 2 mu dot s psi s. So here note that if you differentiate, so in this argument here, that's what produces the ls here. And the other one is just the explicit time derivative. So this function satisfies this bound. So essentially by Groenval, you conclude that nu s is bounded by e to the minus lambda s minus 2 mu s psi of 0. And now psi of 0 is given by e to the minus lambda s minus 2 mu s. And now we have the Dirichlet form at 0. So I don't put it there. And I don't have a, so I have a C0 dot here. But remember, C0 dot, so CS dot is the heat kernel, right? So C0 dot is just the identity. So this is just the identity. We can remove it. And that's it. So summary is the entropy with respect to, oops, the measure nu of f is bounded by 2 times the integral from 0 to infinity of e to the minus lambda s minus 2 mu s ds times the standard Dirichlet form. And this is just 1 over gamma, the Log-Sobolev constant, or it's a bound on it. Okay, so the proof is very much like the Bakry-Emery argument, with the twist that the measure is changing as we go, and that all estimates are in terms of the renormalized potential rather than the original potential. Okay, so so let me remark 2 aspects that are basically obvious from the proof, but they're perhaps interesting to observe. First of all, the same proof also shows the Log-Sobolev inequality for the renormalized measure. Nu s. And the constant is roughly similar in typical applications, because the main contribution, so basically what happens in the renormalized measure, the integral doesn't start at 0, but it starts at s or something like that. But in the typical contribution that we have in mind, the slowest modes are the macroscopic ones, as we discussed in the free field example. So you will still integrate the slowest mode. So the Log-Sobolev constant of the renormalized measure is, well, it depends a bit on what s is, but if s is not too large, it will be similar to the full Log-Sobolev constant, because both of them contain the macroscopic modes. On the other hand, you can also look at the small scales. So it shows the same argument that what I'll call the fluctuation measure defined by, so I call this fluctuation measure, say the fluctuation measure from, depends on an external field phi, and it goes from scale 0 to s, and then it acts on a function f. So this is the fluctuation measure, the this one here. So this is just nothing but the Polcinsky semigroup run from time 0 to, or scale 0 to s, and then evaluated at phi. This defines a measure. So this measure also satisfies the Log-Sobolev inequality. So or maybe it's plural, right? There, for every s we have such a measure. Satisfy, so I guess it's plural here. Log-Sobolev inequalities with constants gamma s, which are much bigger than the full Log-Sobolev constant. And in fact, gamma s is just given by taking the integral from 0 to s of the same thing. So if s is small, this integral is going to be small, so gamma s is going to be huge. What this encodes is that the small scales, just as in the Gaussian case, the small scales equilibrate quickly. So this is what we physically expect, right? And that's part of this proof. I mean, so these statements for the renormalized measure, in particular for the fluctuation measure, they're they're not part of the final conclusion, but somehow this intuition is essential, or is underlying this proof that somehow the small scales equilibrate very fast, that they move very fast compared to the macroscopic ones, and you can also make this precise in the sense that you can decompose this measure in terms of these Dirichlet forms of the small scales and the large scales. Okay, so right. So okay, so let me summarize once more.
Sorry, Roland, there are two things. One, there is a question from Trishan. Maybe you want to look at it
square
now.
missing. We've done that already. Just as a reality check for me, how stable is this under a different choice of C dot S? It is, you can use different choices of C dot S. And in fact, in the paper, we included another possibility, which it turns out that the heat kernel works by far the nicest if you go to this part of the argument, right? So here you differentiate the heat kernel twice. You see you recover the heat kernel back, and the argument closes beautifully. So here in this step, using the heat kernel was extremely useful. It's not necessary. You can play with sort of similar arguments where maybe you don't change the Dirichlet form in this part of the argument and fix it and change it somewhere else. So we did these variations in the paper. What you get is not as good as this criterion. You get sort of versions of what we get here. But instead of having the QS on both sides of the Hessian of VS, you only have it on one side, and then you symmetrize. And that's a worse criterion. So for example, in the case of the Sine-Gordon model, you can see that if you do that, that can't work up to 8 pi. While this one, we can only check up to 6 pi, but in principle, it seems to me that this criterion is good enough that it could work up to 8 pi. Well, if you do the symmetry, if you don't have it symmetrized with the QS on both sides, you're losing something. You have a weaker, or you need to check a stronger condition, and you have less smoothing. I mean, having the QS on both sides gives you more smoothing. And so if you use a different decomposition, you get something, but not as good as this one.
Okay, then I had a question myself about this last remark you made about equilibration of different scales.
Yes.
I mean, is this, then you say you can make it precise, but.
Okay, so in fact, this is a good, I mean, okay, let me say it this way. So here, indeed, we see this at the level of the decomposition of the invariant measure and the Log-Sobolev constants. It's a different question to make this precise at the level of the dynamics, and which is, I think, what you're asking, right?
Yeah.
And in fact, we've thought about this, and we haven't quite succeeded in doing this, but believe very much that you can do it. Okay, so maybe we can talk about this.
Okay, maybe my intuition is wrong, but if you look at the dynamic and then you just look at the small scale, it's not even Markov. I mean, if you just take a subset of scales.
Exactly,
then,
yeah, exactly. That is part of the issue. But somehow this gives, I mean, maybe this is the point we can discuss after the lecture. Is that okay? Can we come back to that afterwards?
No problem.
It's maybe a bigger topic than but anyway, yes. Okay, so here, what I've claimed here is at the level of these decomposition of the invariant measure and the associated Log-Sobolev constants. Okay, let me summarize pictorially what is happening here. So we're interested in the equilibration of the Glauber dynamics. So we want to see as time evolves, how quickly does the relative entropy nu t with respect to nu infinity go to 0? And the starting point to do that is this, the Brun identity. We can express, oh, this is not phi, this is an I. We can express the change of relative entropy in terms of explicitly as this so-called Fisher information. And the goal is to estimate this Fisher information by below, again, by the relative entropy. So to close the argument, use a Grunwald argument to get the rate of equilibration. So this step involves Glauber dynamics. It involves time and thus Glauber dynamics. Now, to actually do that, we use a different dynamics. So we maybe, so this is Glauber. So now we, at this point, we move and scale instead. So we look at h nu t, but then we see how it changes as we vary the scale. So now, Hendrik, you see, I mean, this is the two, so we look at what happens, we have the measure at time t, and then we change the scale. So, and again, there is a kind of De Bruijn identity where this, relative Fisher information also changes. So in this, I call this the Polcinsky dynamics. The renormalization group dynamics, if you wish. And then, to close the argument, we do the interpolation in the Bakri-Emery argument, which works at the level of these Fisher informations using the RG dynamics. So, so this should again be blue, but we look at, so this is what happened in the proof, right? So we look at this, see that it, that we can get an estimate suitable for a Grunwald estimate in S in this scale by scale dynamics. So from that, we see that IS sorry, the TS, and so here we have nu infinity S. So this should, so I guess this is nu, the infinities are in the wrong spot. So the nu infinity doesn't really depend on T because it's just a delta. So maybe I'll remove the T here. So that this relaxes in this scale way. So here in this Grunwald argument, this relative Fisher, the scale-dependent relative Fisher information reduces to the original scale 0, 1. Sorry, something. No, sorry. This was correct after all. Okay. And so we plug that back into the estimate for the UT. There's a lot of indices here. It's easy to get confused. So we get using this scale interpolation.
Yeah, so, sorry, I don't understand the first inequality. Sorry, the second line, where the first arrow. You have I0 on the right-hand side, I0, nu 0 t with respect to nu st.
Sorry, there is
0, maybe.
Yes, this should be 0. Thank you.
Okay.
Yes. Right. So, I mean, the point is that even though we're looking at the change of these S-dependent quantities, the ultimate estimate will be in terms of S equals 0, which is exactly what feeds into the original Log-Sobolev inequality, which interpolates in time. So somehow the Dirichlet forms, they evolve differently as we go through scale, but at the end point, the two match. And so we can switch from one dynamics to the other. And so from this, I wanted to draw this picture, and I guess I'll need the next slide for that. So here we're back at the Glauber dynamics. And so the picture I wanted to draw is, so we start at time 0, then we want to go to time infinity. We have this measure nu t, this measure nu, the invariant measure. And then, so I guess this would have to be, all of this would have to be red. And then we use, somehow we go orthogonally in the scale directions, and we have nu t, nu ts. And so here this is time, and this is scale. And so as we move through time, we always interpolate and scale to close the estimate. So that's sort of the schematic picture of what's happening in this argument, as good as I can explain it. Okay. So at this point, I wanted to, before taking questions, let me just see, there are none right now, but I wanted to provide some, well, okay, here's an exercise. It's not what this exercise has a solution. It's not too bad, but if someone has a really cute solution, I'd be curious. So take the simplest example you can, finite dimensions. A is Laplacian times the identity, and take a potential V that consists of 2 parts. One is convex and the other one is bounded. So this is a standard example for which the Log-Sobolev inequality is known by, as I explained, by this Hully-Struck criterion for B, for VB combined with a Bakry-Emery for the VC. And so convex, so Hessian of VC is non-negative. And let's assume, makes things simple, that VB is, let's say, bounded in C2. This is then show that Hessian of Vs is bounded by some constant for all S. So this constant is independent of S. It can be negative. So you get the Log-Sobolev inequality from this. Of course, in this case, it's known anyway, but anyway, I'll leave this as an exercise. And if you have a very nice solution, I'm just curious. Anyway. So I guess my time is roughly up.
Oh, sorry, can I ask a question?
This is not an exercise.
Yeah, in the exercise, no, the fact that you're looking at the effective potential, can you remove this hypothesis that V is C2? That VB
oh yeah, I'm sure you can, but basically after any positive time, V is C infinity, right? Because it moves after, according to heat equation.
Yeah.
I think one has to be a little bit more careful then. I think it wouldn't be a problem, but I haven't thought about it very carefully. But I mean, so I'm just, so one way you can prove this exercise is, of course, you can use that there is already a spectral gap or you can use something like the Hully-Struck criterion to do this exercise. But what I'd be interested in is to see if there's a really, if someone has a dynamical way to see that, say, a Hessian that is of this particular form cannot blow up, basically. I mean, so Hessian is allowed to be negative, but I don't want it to go to minus infinity, right? So basically some kind of stability to see this just using like sort of tools like the maximum principle and so on. That would be a nice proof and potential have generalizations to other arguments. That's why I'm kind of curious. Okay.
Yeah, I would have used the variational principle.
Yeah, you can use the variational formula, and then it's not very hard to see it. I was just wondering if you can do it without.
Sure.
So just like the fact that if you have a non-negative one, it stays non-negative. Okay, so yeah, so.
You mean with the Polcinsky equation or with?
Yes. Yes.
Okay.
Yes. So right. Yes. So this VS is, so I'm wondering if there's a proof that only uses the Polcinsky equation. I mean, it's ultimately equivalent, but okay.
Yeah.
Can I ask a question?
Yes.
I just wanted to understand this. So is geometrically your last argument about Bakry-Emery would be just look at the weighted manifold kind of thing, and where the weight actually depends on the parameter S, and then finding, so it interpolates between what you want and something else. And then, because then this kind of condition you have would be just for the weighted Bakry-Emery which have been used.
Yes, I mean, it's sort of, I mean, this weight is the, I mean, as I mentioned at some point, I mean, you can interpret it like this.
Because then you have to change the gradient, which is what you did.
Exactly.
So it's completely consistent with that picture, yeah.
Yeah, I mean, so the observation is basically that you should, I mean, so here you have this, I mean, if you want, you can see it as this flow of the metric. I mean, it's explicit, yep. So it's not a particularly interesting flow, but you start with the standard identity metric on the whole space, and then the metric becomes smoother and smoother, or the unit ball in that metric becomes smoother and smoother. And you only measure with respect to smooth functions at scale S, and there you do everything as, yeah. Right.
And also, I was wondering, so that there have been some work on hyperelliptic diffusions and kind of curvature dimensional Bakry-Emery, whatever you call it, type conditions that would imply Log-Sobolev, and there, instead of modifying the reference measure, you modify the gradient itself. So you're using different functionals with more parameters than usually people used in this business. And the kind of Log-Sobolev you get is slightly different from what you expect. There are some other parameters, but they might capture these different scales of behavior. I don't know. I just thought that if I just
okay. Well, I'm not familiar with that, and
okay, I can tell you later if you're interested. Okay. But it might be completely irrelevant. But I thought that's a different direction from modifying the reference measure.
I mean, so for us, modifying the reference measure is really sort of, I mean, that seems like an essential point, because we want to, I mean, use this idea of renormalization where we have a complicated measure to start with, and then we interpolate in a scale by scale way with an increasingly simple measure that on smaller scales begins to basically, where you don't see the smaller scales anymore, or to replace the measure by one that's equivalent at larger, essentially equivalent at larger scales, but that for which the small scales have been averaged out. And
okay, thank you.
Are there other questions? Okay. Well, if not, maybe you can unmute yourself. I think I didn't muted anybody, so I don't want to unmute people myself because maybe people are doing this. Let's Roland for this lecture. Okay. So session of today it's finished. Hendrik, you want to say something particular?
No, just thanks a lot to everybody, and looking forward to